Oops. All right, so last time we had looked at this really cool technique for routing, for taking a collection of messages from a set of sources to a set of destinations, with the goal of minimizing congestion in the network. Our model assumed that we had a network where you could only send one message across a link per synchronous time step, which meant that if a lot of messages tried to cross the same link, there would be a lengthy delay and it would take a lot of time to actually deliver those messages. And we homed in on the specific model of message routing in a hypercube. It's a particular popular network shape. It's one where each pair of nodes that are adjacent in the hypercube geometry are connected by a pair of links, one in each direction. So you can send messages in opposite directions in the same, one message in each direction in the same time step. And we saw that this hypercube that we were routing in had n equal 2 to the d nodes. It had diameter d, right? So, of course, d is a lower bound on the time that it will take to route things, since sometimes you want to send messages from one end of the hypercube to the other. We talked about bit fixing as a particular simple routing mechanism. We showed that if you use it deterministically, as with all deterministic algorithms, it has very bad performance. You can always construct a permutation routing task where there's a lot of congestion, many paths that all use the same link, and that leads to very slow delivery of messages, right? But we analyzed the sort of random instance case, right? And I argued by symmetry that the expected number of paths using a link was about a half, right? And so I argue, and that these, we sort of express this as a sum of independent random variables. And so we were able to apply the Chernoff bound to conclude that with high probability, the number of paths per edge was order log n, which is order d, right? And therefore, if you look at the path that a particular message takes through the network, if it's using bit fixing, it's only going to traverse d links. At each of those d lengths, there are perhaps log n other messages that are trying to use the same link, and so a particular message will see a delay of at most log n time steps at each link, which would mean order log squared n time to get all the way through its path, right? Right? I'm just recalling this all into our memory since it's been so long since the last lecture. So this is already way better than we could achieve with a standard, with a deterministic algorithm. But I then claimed a stronger statement, right? I used a similar analysis to look at the number of paths colliding with my path not with a particular edge on my path, but with colliding with my path at all, sharing any edges, however many it is, was order log n with high probability. Okay? And this was, again, by arguing that I could apply the Chernoff bound to a sum of independent indicator random variables, right? This took a little extra work, but I made that argument. And I then just claimed that each path that collides with mine is only going to cause one time step of delay, even if that path shares many, many steps with mine, many, many links. And based on that, I was able to derive order log n delay, which of course means that we have asymptotically optimal routing, right? The diameter is order log n, and it takes us order log n time to route messages, okay? And then, of course, the big cool result at the end was that we could apply this also to worst case by routing each message to a random midpoint before sending it on to its ultimate destination, right? This was the didn't take any technical skill, but was perhaps the craziest and most creative part of this work, okay? Was that this is a simple way to transform the worst case into the random case, so all of our randomized analysis applies. Yes? And this is where we left off last time, but that means that I still have to fill in for you this assertion that I made, that the total delay is going to be determined by the number of paths that collide with me, regardless of how many steps we share. And it's kind of unfortunate that I have to do this because this is not about randomized algorithms at all. This is an entirely deterministic argument, right? We're going to fix the paths. We're going to fix the path that I'm taking. We're going to fix the paths that collide with me. And I'm going to argue that under, pretty much any greedy routing scheme, like the bit fixing one that we're using, the total delay is just determined by the number of paths that collide with me. And this uses what's called a lag argument. And these show up all the time when you're studying routing, particularly when you're doing routing in synchronous parallel machines. There's a lot of work on that. Gaulian-Brebner isn't the only thing. The idea is that we're not literally going to prove that each path that collides with me it's actually not true that each path with me that collides with me only causes one unit of delay. But we are going to show that that's true in aggregate, that we can blame each unit of delay on a different path, okay? So that the total delay is at most the number of paths. And I will emphasize here that that there is no randomization going on. This is a worst case argument. Okay. So I'm going to leave for you as an exercise that once a packet, let me try again. I'm going to fix a particular packet and its path, and I'm going to look at the delay caused by other packets. And so my first exercise I'm going to leave to you is just to show that once a packet leaves my path, it doesn't return. And again, this is just is a feature of the bit fixing process, right? A packet leaves my path when it fixes a bit differently from my path, which means that it's headed to a different place. And you just have to argue that it's not going to return to my path in order to get to that different destination. It's going to stay different. Okay? So let's call my path rho sub I, I'm packet I, which is a series of edges. Okay. And what I'm going to do is charge each unit of delay to a departure of another packet from my path. Okay. From my path rho I. Okay. So we charge the delay to a packet that leaves. The packet never comes back. It can't be charged again. So we only have one delay per packet that leaves my path. Okay. So in order to do this, I'm going to define that a packet waiting to follow edge EJ at time t as lag t minus j. And lag is just a label for sort of kind of how long it's been held up on my path, right? So this makes perfect sense when you're talking about me, right? If I was going to just traverse my path and nobody was in the way, it would mean that my lag is always 0 because I'm trying to traverse the jth edge in the jth time step. If I get held up, my lag will increase. I'm going to use that same lag label for every packet that is traversing my path, even though it has a different destination. Okay. And then my delay is my lag when I cross the last edge in my path, E sub k. Yes? So let's understand what causes my lag to increase. Okay. When my lag or delay increases, why is that happening? Yes?
Some other packet trying to...
Exactly. Not just trying, but succeeding. Some other packet uses the edge I want next. Right? So what this means is that when my delay rises, or my lag rises from L to L plus 1, some other packet also has lag L because it has to be fighting with me. But its lag stays L because it actually moves forward to the next step. And so its lag is still L. Okay? So now we're actually almost done. What we're going to do is consider the last time t prime where a lag L packet is present. I should say another on my path. Okay. So, these packets are on my path for a while. Eventually they leave. Let's just consider the last time at which some other packet has lag L. Why is it the last time? Why don't we continue to have a packet with lag L? That packet is still there in the next time step. Why doesn't it have lag L? Yes? Exactly, right? Lag is defined when I'm on the path, right? So, in the next time step, that packet leaves the path. It is no longer fighting with me. Okay? Sorry. Let's call that packet W. Okay. So I'm going to charge my increase from lag L to lag L plus 1 to W. And that's basically the end of the argument, right? Because the only reason that I can have lag L, right, or the only reason my lag can increase from L to L plus 1 is that there's another lag L packet. So this is a non-empty set, right? When I'm talking about the last time where there is a lag L packet, there are other packets that have lag L. Okay? Now I'm not going to charge my delay to the packet that actually held me up, but I'm just going to wait until the very last packet that has lag L departs the path, and then I will charge it to that packet. And that ensures, right, you can imagine that, the bus directly in front of you, right, it keeps moving forward and then getting held up by the bus in front of it, right? And so it holds you up over and over again. So I don't want to charge to that packet that's holding me up because it might hold me up multiple times. But if it's holding me up multiple times, that's because some other packet is holding it up. And some other packet is holding that packet up. And you just keep moving down the line until you find the kind of root cause of all those delays, and you can charge to that, to that particular lag number instead of charging to a particular packet. Or you charge to the packet that has that appropriate lag number. Okay? So that's basically the whole argument for why each path that collides with me only contributes one step of delay in my path. And so the total delay I experience is bounded by the number of paths that collide with me. And that finally closes out the story of randomized routing. Any questions? All right. I showed you all the cool stuff last time, and that's when we talked about the questions. Yes?
I talked about this last time, but we're saying that overall the runtime goes long.
Yes.
So then,
with high probability.
Yeah,
Always have to add that qualification when you're talking randomized.
But then I guess, because we're saying that the number of paths outside of one path is no longer having. So then, they're like, I guess.
No, there are two to the D paths. And this is important, right? So when I say with high probability, right? So let's get this down as a note, right? It's important to know what parameter you're talking about, right? And here I used a Chernoff bound. I talked about log n, right? And similarly, I'm saying with high probability in n. So d is a helpful parameter, but it's not the one that I'm using for any of this discussion, right? So it's with high probability in n, which means probability n to the minus O of 1, or let me put it a different way, n to the minus k, where you can make k whatever you want by fiddling with your constants. Now, why is that important? Because as you said, what I proved was an analysis for a single path, right? However, the reason this works is that there are only n to the order 1 paths. It's actually about n log n, but what's important is that it's n to the order 1. And therefore, by choosing my constants, I can set the probability of a loaded path to be so small that the probability of any loaded path is still inverse polynomial by a union bound. Okay, and again, you need to get used to this. This is how all of the arguments work in randomized algorithms, is that you make a high probability argument, and then you proceed to happily union bound that high probability argument over a polynomial number of events. You can get tripped up if there is more than a polynomial number of events, right? Sometimes there are exponentially many events to worry about, and then you can't use this high probability argument. And you do have to remember what your parameter is, because some parameters may differ by an exponential. Okay? That's a good thing to ask about. Other questions? Okay. So today's topic is again about load balancing. And it's, for me, like really representative of a certain kind of beauty in randomized algorithms, where the key insight is incredibly simple and intuitive. And then you have to work like crazy to prove that it's true. So I'm going to give you the sort of fun part of this lecture in 5 minutes, but then the rest of the lecture is going to take up the proof. Okay? So we're going back to good old balls and bins. I'm not going to tell you what the title of this lecture is because that would give away the trick. Okay, but we'll get there soon. So remember, we're going to focus on this canonical case of throwing n balls into n bins as a load balancing goal, right? In a perfect world, every ball would get 1 bin, and you would have perfect load balance. And this can represent anything, right? It can represent work being assigned to processors. It can represent people being assigned to jobs. It can it just goes on and on. This is a really general abstraction of load balancing. Yes? And there are all sorts of constraints you can put on load balancing. Those of you who took advanced algorithms with me, this is part of scheduling theory. It fits in very naturally there. And there are tons of algorithms, but a lot of them require a lot of coordination between different bins, right? If you just take n people and tell each of them to do a job, then you're probably going to have a bunch of people all deciding to do the same job and other jobs going undone, right? So they all have to talk to each other and figure out who's going to do what job. It can get very expensive, right? A good alternative to this is randomization, right? So if we just put each ball randomly into 1 bin, we get an expected good behavior, right? The expected number of balls per bin is equal to 1, which is the ideal, right? Unfortunately, we don't get to work with just the expectation. We have to worry about deviations from the expectation, right? And we could invoke our tail bounds, right? So what does the Chernoff bound tell us about the maximum load of a bin, the maximum number of balls that will land in any bin? Yes? So we're going to get there, but what does the Chernoff bound tell us? So remember, with the Chernoff bound, you've got one set of bounds that you can use for small deviations that involve an epsilon, right? But here we're actually thinking about the large deviation case, right? And the general Chernoff bound rule is that the probability that x is bigger than some large c times mu is at most to the minus c mu. Okay? Basically exponentially small in the value of the bound, right? So here we have c mu, and we just put it into the exponent. So what do we need to do in order to make this small enough to be useful? If we want a bound that applies to all n bins. Yeah? Exactly. If we make this order log n, right, then this becomes n to the minus order 1, which means that with high probability, all bins have order log n balls. Right? Now, as you mentioned, if you look at it exactly, you can show, and I did this a few lectures ago, so I won't repeat it, that actually order log n over log n is a high probability bound on the maximum bin size. Okay? And you just do that by plugging into the binomial, by looking at the binomial distribution for these parameters and showing when it's less than n to the minus order 1. Okay? So, pure random assignment works pretty well. Okay? But what if you want to do better? So, I mean, until nobody really thought about this problem until the 90s, I think, because it didn't seem like there was anything obvious to try. Okay, if you were staying in this model, but I think it was Azar, Broder, Cardolin, and Upful had this really nice paper called The Power of, well, I won't tell you what it's the power of because we have to figure out the trick. So we don't want to coordinate across all these different bins and make some sort of global plan. But suppose that you're a ball, you're being told to go to a bin, and you want to be a little bit smarter than just picking a random bin. Can you think of something that does not take a lot more work, but has a chance of giving you a better situation, at least for yourself? Yes?
That's the person before you.
Okay, so stay away from where the person before me went. That seems like a good heuristic and only requires asking one person. But it's going to be very localized, right? It takes one bin out of contention, but there are still n-1 bins that, you know, God knows what's going on there. Yes, purple sweater. Yeah, maybe you sort of look at one bin and decide, oh, that's too popular, maybe I'll try another bin. Okay. Now that's a little too sequential. But what they proposed is just looking at two bins. Okay. So their proposed load balancing procedure is, instead of looking at just one bin, look at a pair of bins and go to the smaller. Okay, for each ball in sequence. Look at two bins and go to the smaller one. Pretty tiny change, right? You just need to look at two bins instead of one bin. Surely this can't have much of an effect on the outcome. But maybe it gets you a little better. Right? Any guesses on how this might improve things? I mean, maybe if you're looking at two things, it cuts your max load in half. That would seem kind of plausible, right? Yes? Exponential improvement, maybe. I mean, that's asking for a lot from just making two choices. Why? What would sort of intuit that?
I mean, I don't know, but also like.
You're just getting used to exponential improvements in this class, so you figure I'm going to pull out another one.
Yeah.
Yeah?
But I guess like a rough definition, kind of like you get all block n like a lot, like if one bin's kind of getting a lot, so like picking or like a few bins get a lot, kind of like randomly, then I guess like they have to kind of they bins will kind of confuse it, I guess, such as like choosing off the
Yeah, there's some good intuition there. That, like, yeah, I mean, you can actually prove that this log n over log n is a theta, right? That there is going to be a bin with this bound, but there aren't going to be many of them. And so you could hope that if you're picking two bins, you're very unlikely to pick a bad one twice because they're rare. Yes? So let's try to formalize that a little bit. Now I actually have paper notes. So we know clearly only n over 4 bins can have 4 balls in them. Right? So if I pick 2 random bins, what is the probability that both have 4 balls? Yeah? It's less than 1 over 16, because these are 2 independent choices. And again, this is me using randomization. This is not about the random input or anything like that. I'm just choosing 2 random bins. Each of them has only a quarter chance of having 4 balls, so there's only a 1 in 16 chance that I'll have 5, or that they'll both have 4, right? So I only become the 5th ball with probability less than 1/16, which kind of tells me that there are, in expectation, the number of 5 high balls is at most what? Yeah? N over 16. Okay, but if there are only n over 16 balls that become the 5th ball, that means that the expected number of 5 high bins is less than n over 16. Yes? But now what do I do? Yes? Exactly. The probability that I pick 5 high bins is at most n over 256, right? And the probability of 6, and that is equal to the probability that I get a 6 high bin. So skipping over steps, the expected number of 6 high bins is less than, this is 1 over 256, and the expected number of 6 high bins is only n over 256, right? So each time I go round this argument, what do I do to the denominator? I square it, right? So the number of, just sort of by induction, the expected number of k high bins, or k plus 4 high bins, is at most n over 2 to the 2 to the k, or something like that. Yes?
How about using like the expected value of the number of like bits and like 5 posts?
Oh, are you getting nitpicky over my lack of rigor? Are you getting picky about my not being formal enough? I mean, this is a computer science class, not a math class. No, but I will in fact spend the next 45 minutes formalizing this argument. Okay? This is just to get the intuition across. Okay? So, n over 2 to the 2 to the k. So, when is this tiny? Yes? Right. So this is tiny at k equal log n. So you were in fact correct. Yet again, we have an exponential improvement in the load. It's perhaps less amazing because it's from log n to log n, but it is nevertheless an exponential improvement in the load. Okay? Good. So this is the whole intuition for why this works. Now we have to prove it. Why is it hard work to prove? What are the flaws in my intuitive analysis? Or the things that we have to make more rigorous? Yes? Good. So, issues. 1, treating expectation as reality. Sadly, this does not work, right? I always expect to be on time for things, but somehow I'm not, okay? There's another big problem. This one is more subtle. The problem is that I made this whole argument about having only n over 16 balls at height 5 or whatever, right? In order to make that argument, I looked at all the balls and where they ended up. I have just created a massive conditioning, which I proceed to completely ignore when I ask about the balls of height 6, right? My whole argument about balls of height 6 has to be conditioned on what happened when I was thinking about balls of height 5. Okay? So the analysis bounds one layer the assumptions about the previous layer, which means that we have to cope with the conditioning of one argument on the next. Okay? So those are the things that we are going to have to address in order to make this argument formal. But I will reassure you, this argument is in fact correct. We are going to end up with the intuitive result. We're not going to have to change it to make it correct. All right? So any questions before we dive into that? Yes? Great question. Let me save that for the end so that we don't finish the lecture having just gone through a 45-minute proof. Okay, let's look forward to something fun and interesting at the end. The proof is actually also interesting. It lets me introduce you to some really cool techniques or at least one really cool technique in the analysis of randomized algorithms. Okay? All right, so let's get started. So first thing is dealing with expectation. We're going to need to move from expectation to tail downs, right? High probability results. Okay. Oh, by the way, this thing, I don't know if how many of you have seen it, but a lot of people define happiness as the gap between expectation and reality. So it's sort of interesting to have that up in the slide. Okay, so let's define VH to be equal to the number of bins of height at least h. In other words, there are at least h balls in the bin. Okay. We know, as our base case, that V4 is at most n over 4, and this does not condition anything. It's just true, right? Now, I'm going to write y sub t equal 1 if the teeth ball that I insert has height. I'm working off of the base case of 4 high, so I'm going to do this analysis about 5 high, and then we will argue that the same analysis works for any height. Okay. So we're looking at height 5 bins, and we're going to consider one ball at a time and ask when it has height 5. Right? And we said that the probability of yt was less than or equal to 1/16. We argued, as a result, that the expectation of V5 was less than or equal to n over 16. Right? What we would like to do, but I'll put a question mark here, is actually, maybe I shouldn't do this. This may be too easy if I'm looking at height 5. Let me think for a second. No, this is okay. So we want to use Chernoff to argue that V5 is less than, say, twice its expectation with high probability. Okay? But I claim that we can't right away. Why can't we right away make that assertion? Yes. Sorry, which is not directly a sum of indicators? V5. Fair. So you're right in the sense that this probability here is counting the number of high balls. But if I can show that the number of, if I instead were aiming to show that the number of tall balls, that land at height 5 is at most n over 8, right? That will yield this, right? So can I argue that the number of balls of height 5 is at most n over 8 by the Chernoff bound? Or is there an obstacle to that? Yes?
The issue is that, looking at the heights, the balls aren't independent from each other.
Good. The problem is that the yt are not independent. So can we fill that in a little bit? What makes the yt not independent? Well, suppose that I have this huge series of yt's, right, that are all 0, right? None of these balls are ending up high. What does that tell me? Well, it tells me that more of them are being spread around. And so there are going to be too many bins that are nearly high. Okay? Which is going to increase the chances of other balls ending up with two choices that are both too high. Okay, so in a sense, these YTs have a correlation that's causing problems for me. Okay? Yes?
Maybe we can show that, like, V5 is less than or equal to like this other random event.
Good. So that's the point, right? We cannot use these YTs with the Chernoff bound because they are not independent. But the Chernoff bound is so useful that what we're going to try to do is create some other independent variables that we can use the Chernoff bound on. Okay. But notice, by the way, that even though the YT are not independent, their dependence, it kind of should be going in the right direction. Like, if one ball is high, that actually should make other balls more likely to be low. So it seems like it should decrease the chances of an extreme deviation, right? And I'm not going to prove a negative correlation. That is something that I asked you to do. That wasn't an optional problem in the homework. I'm going to show you a different technique for getting around this problem. The lemma that I'm going to use is stated pretty abstractly, but I'll fill in I'll attach it to our concrete case. Let me have some variables yi, and each of these yi's is a function of a sequence of underlying variables. So basically, you generate some x's, x1 through whatever, xn, and then I generate y's by looking at prefixes of the x's. So the y's are kind of a derived phenomenon from the underlying x's. Okay. And notice that to generate the next yi, I add in one more x. Right? Each time I'm generating a new y, I'm bringing in one more x to its function. If the probability that yi equals 1 conditioned on all except for the last x, right? So again, the way to think about this is that in order to generate yi, I already had x1 through x minus 1 for generating yi minus 1. Now I pick one more xi to yield yi, right? So if the probability that I choose that xi that makes the yi be 1 is less than p for all I, then the sum of the yi's is stochastically dominated by that binomial distribution of independent random variables with probability p. Yes?
So, I guess I'm wondering, I can see how the ball, like, the YT fine, but, like, no matter what happens, like, Z4 is that's not
Correct.
I guess, like, why does that influence matter if it's always like down
It's true that the individual probabilities of a YT being large are bounded because there's only only n over 4 bins of height 4, right? But you have to worry that maybe they all end up high in the same event, which ends you up with a lot of high balls, a large deviation from the expectation, right? We're trying to show that we don't have a large deviation from the expectation, right? If you think about it, there could be as many as n over 5 high bins if all of the balls decide to concentrate on the same bins of height n over 4. And the dependency means that you can't immediately rule that out. Okay? All right. So people remember what the binomial distribution is? People remember the definition of stochastic domination? That essentially, for any threshold, right, the binomial distribution is more likely to go above that threshold than your distribution. Okay? And that would imply that the Chernoff upper bound applies to the sum of the yi's, even though they are not independent. Okay? So this is just one nice way to apply a Chernoff bound to dependent random variables. And it's pretty clear from this sort of general description that the yi's appear quite dependent, right? Because yi and yi plus 1 are both determined by these xi's that they share in common. Yi plus 1 just has a little bit of extra randomness coming in it. Yes?
When we say given x1 to xi1, is that some different values?
That's conditioning. Yes, that's right. That's
Doesn't get any set of values.
exactly. When you condition on random variables like this, you're conditioning on any possible values of those random variables. Good question. Yes?
So this is true for arbitrary y and x on arbitrary functions of the term y and x.
Correct.
And all we're saying is that if all of the x's from 1 to I minus 1 are 1, then the probability that y is 1 is less than
Yes. All the y's, not all the x's, right? All this is saying, intuitively what this is saying is that there's enough new randomness coming in when you choose xi plus 1 to define yi plus 1. There's enough new randomness coming in that sort of ensures that the probability that y is 1 is less than or equal to p regardless of what came before. And that is enough to let you treat the sum as stochastically dominated by these coin flips. Perhaps it will be more obvious once I prove it. Okay. The proof uses one of my favorite analytic techniques, what's called a coupling argument. A coupling argument is a way of kind of taking some random variables that are hard to understand and connecting them to a different set of random variables that are well behaved, and saying that you can understand the behavior of the complex random variables by looking at what's going on with the well behaved random variables. Okay, and I'll use this several times during the semester. Let's imagine generating a sequence of random variables zi, which are different from while we are generating the yi's. Okay, and how do we generate the yi's? Well, we generate the yi's by generating the x's one at a time and reading off the corresponding y's using the function. Yes? Okay. Oh, sorry, just to ground this. What are the yi's and xi's here? Well, you should think of the xi's as the positions of the balls, right? So you're thinking about balls 1 through I minus 1 being placed, and that determines the heights, the VH variables for balls 1 through I minus 1, right? Now I'm going to put in the next ball, which gives me an xi, and that determines whether that ball is too high. So those are the y's. Yes?
By the way, when you say stochastically dominated, do you mean on the right tail distribution?
Yes. Stochastic domination says that the probability stochastic is one way, right? It says that the probability that let me use some different numbers. R is less than K is less than the probability that S is less than K. It's only one direction. All right, so now, again, these y's are these height variables, complicated to understand. I'm going to generate another sequence zi in the following way. First, check the value pi, which is the probability, or these should be t's. now let's call them i's. The probability that yi is equal to 1. Sorry, I'm switching inconsistently from t to y, but they're both the same index, right? Because I'm just sort of going up by one ball at a time. Okay? So, I've inserted the previous balls. This creates a certain probability that yi will be 1. This is a thought experiment only, right? Obviously, my algorithm doesn't know what it is, but there is a pi. Yes? So this is some messy function of x1 through xi minus 1. Okay. Now, I'm going to generate. Oh, what do I know about pi? Well, I know that pi is less than or equal to p. Okay. So now, I'm going to generate my yi. And if yi is equal to 1, I'm going to set zi equal to 1. This is the coupling. I'm intentionally making y and z not independent of each other. Okay. Else, if yi equals 0, then I'm going to set zi equal to 1 with probability p minus pi over 1 minus pi. Okay. Why did I pick this number? Well, what is the probability that zi equals 1? Well, it's the probability that yi is 1, which is pi, plus the probability that yi is 0, but I set zi equal to 1 anyway, which is 1 minus pi times p minus pi over 1 minus pi. These cancel, and so I have pi plus p minus pi. So the probability that zi is 1 is exactly p. I will let you digest that. So what is cool about this? What is cool about this is that I've taken away all the messiness of y. I take away all the messiness of not knowing what is pi, right? Z is just a coin flip with probability p. Okay? And it is a coin flip with probability p that is independent of everything else, right? It doesn't matter what else happened in history. Zi is 1 with probability. Sorry, I said too much. Notice that yi is less than or equal to zi. This is the coupling, right? I've carefully set things up so that whenever yi is 1, zi is also 1. So zi is never smaller than yi. Okay? This means that the sum of the yi's is less than or equal to the sum of the zi's. Again, not probabilistically, this is just fact. Okay? But the key is that each zi is independent of the other z's. Because its probability of being 1 is just p. Doesn't matter what happened before. Its probability is not changed by the values of the other z's. Therefore, it is independent of the other z's. Yes? So what distribution does the sum of zi's have? Yes? Exactly. The distribution of the z's is just b of np. N independent coin flips with probability p. Okay? So this is my favorite kind of argument because it has no math to speak of, but is really deep. And you really have to sort of ponder it for a while. Like how is this possibly working? What is going on here, right? But essentially, I've generated a bunch of simple random variables that upper bound my simple independent random variables that upper bound my complicated dependent random variables. And so this is exactly the stochastic domination argument, right? Or sorry, this is the stochastic domination. Right? The z's look like b of np, but they're always bigger than the sum of the y's. Therefore, the sum of the y's is stochastically dominated by b of np. Okay? Yes?
I guess I'm like, I was gonna ask like how would it be based on
Exactly. That's the point, right? Dependence arises when the probability of something changes because of what came before. But the way we've defined the z's, their probability doesn't change, no matter what happened before. So they're independent of each other. Okay? All right. And now we can apply this, right? If we apply this to our balls and bins, we can say that each ball has height 5 with probability at most 1/16, right? Regardless of the past. Because this is just using the fact that there are n/4 balls of height 4, bins of height 4, right? So each only has height 5 with probability 1/16. So these are the PIs in my abstract lemma, right? So the sum is bounded by b of n comma 1/16, thanks to our lemma. And therefore, we can apply the Chernoff bound and say that we have at most n/8 of them with high probability. Okay? So you may wonder why I'm happy to just double things here, but I'm creating slack by doubling, but meanwhile the bound is squaring, so the doubling doesn't matter. It's negligible compared to the squaring. Yes?
Do you just like plug it into the Chernoff bound just like so we can see what the
So at this level of Chernoff bound, right? Remember, the Chernoff bound looks like e to the minus epsilon squared mu, or 2 to the minus 1 plus epsilon mu, depending on what you're looking at. So either way, it's sort of exponentially small in mu, right? Sorry, this is for a 1 plus epsilon times mu deviation. So I'm basically setting epsilon equal to 1, right? So it's basically e to the minus epsilon mu, e to the minus mu or 2 to the minus 2 mu. And mu here is like n/16, so it's exponentially tiny chance of deviation. Okay. All right. Let's take a short break to let your brains unexplode. And then I will address the second concern around dependency between different layers of the analysis.